We're continuing with the back page of the Chapter 5 test morning review. This is number 3. Position of a particle moving on the x-axis is given by x of t. Write an expression for the velocity. So we look to our position function represented by x of t. To get to velocity, we're going to find the first derivative, and we look to see what rule we need to apply. We have e to the u here, so we can just go through the rule for e to the x or e to the u, and then this is just power rule for polynomials. So 4/3, the coefficient is just going to stay put. E to the u is e to the u times u prime, so e to the 3t times 3, and then 8t goes to 8. So there we have our velocity function. Write an expression for the acceleration. So acceleration is the second derivative of x of t, and it's also the first derivative of velocity. So we can just find the derivative of velocity, and that will take us to acceleration. So again, we have e to the u. So e to the u becomes e to the u times u prime. The derivative for 3t is 3, and then 8's a constant, so 8 will go to 0. Clean this up a bit, and we have acceleration being 12e to the 3t. Okay, for part C, for what values of t is a particle at rest? Particle is at rest when the velocity is 0. So we can just take the velocity function, set equal to 0. We can then try and solve for t. So I'm going to bring the 8 over to one side, they're both going to be the same sign once the 8 goes over. So 4e to 3t equals 8. Now we just have to solve for t. So divide both sides by 4, and I get 8 divided by 4, which is 2. Take the natural log of both sides. So natural log of e to the 3t is equal to the natural log of 2. Natural log of e to the 3t means that 3t can come down. Natural log of e goes away. We're left with 3t equals natural log of 2. Solve for t. So t is natural log of 2 divided by 3. Part D, find the velocity when t is equal to 3. So if we want to find the velocity, we can simply plug 3 into the velocity function. So 4e to the 3 times 3 minus 8. So 4e to the 9th minus 8 is going to be the velocity at that moment in time. Find the acceleration when t equals 3. So just plug 3 into the acceleration function, 12e to the 3 times 3, 12e to the 9th. At t equals 3, is the velocity of the particle increasing or decreasing? Now, we're not asking for the speed, we're asking for the velocity. Is the velocity increasing? So this is referring to acceleration. In other words, is acceleration positive or negative? So if we look at acceleration at t equals 3, it looks like acceleration is positive, so velocity is therefore increasing because acceleration is greater than 0. Okay, for G, is the speed of the particle increasing or decreasing? Now, if we want to determine whether the speed is increasing or decreasing, this is where we have to now compare signs at 3 for velocity and acceleration. So looks like velocity is positive. This is going to be a large positive number. This is also positive, so they're both the same signs. That tells us that the speed is increasing, right? If velocity and acceleration have opposite signs, then we know that the speed is therefore decreasing. But in this case, same signs mean increasing speed. Okay, for number 4, find dy dx is if natural log of yx equals y squared minus x cubed minus e. We have to go through a series of rules here. One is we have to go through implicit differentiation since we have x and y's mixed together. And also I'm going to take advantage of the fact that we can use product property for natural logs to expand. So we can simplify this expression a bit. So let's do that first. Let's expand. So natural log of yx going through product property. Natural log of AB is natural log of A plus natural log of B. So in this case, natural log of y plus natural log of x. And then rewrite the rest of the equation on the right. All right, looks like everything is ready and set for us to now apply implicit differentiation. So implicit just means that we're going to find the derivative of each term, and then if we happen to come across finding the derivative involving variable y, then we find that derivative and we have to attach dy dx. So natural log of y becomes 1 over y times dy dx. Natural log of x becomes 1 over x. Y squared, power rule, becomes 2y, but because we just involve y's derivative, we have to attach dy dx. X cubed becomes 3x squared. E is a constant, so e goes to 0. So now it's just a matter of trying to get dy dx by itself. So I'll move the 2 dy dx to the left side, and then move the 1 over x to the right side. Here I can factor out the dy dx. Once I factor that out, then I'm closer to getting dy dx by itself, because the only thing left to do is to move that bracket expression in to the right side of the equation. So once that comes down to the denominator, we've essentially found the derivative, which is fine, but we can simplify this further by trying to undo these complex fractions. So what if so one thing that we can do is we can just multiply the entire expression through by the portion that's causing the complex fraction. So it looks like we have an x and y that needs to be taken care of. So if I multiply everything through the numerator and denominator by x times y, then that should simplify the expression so that the complex portions of this fraction will go away. So if I distribute the xy through the numerator as well as the denominator, xy times negative 3x squared becomes negative 3x cubed y. xy times negative 1 over x. Notice the x's cancel out nicely. We're just left with minus y. So look at this. No more complex fraction here. Okay, same thing here. Distribute the xy through. xy times 1 over y. The y's cancel out. We're left with just x. 2y times xy becomes 2xy squared. Again, no complex fraction. And also, the reason why we can do this without changing any expression is that I'm multiplying numerator and denominator by xy. So xy over xy is just really times 1. So I'm not changing the expression that's given in this answer. We're just rewriting it in a form that's a little bit cleaner. And this is especially important on AP exam, where they may be simplifying it further beyond the answer, and you just have to be able to match the answer going through algebraic methods to clean up.